There we go. Now we're recording. So once again, just remember that when you do any of these things that we want to be sure we justify our answer. And I would say justify it with calculus. So make sure you give a calculus justification, not a pre-calculus justification for your answer. So, all right. So here's what we're going to do. I'm going to start off by just taking a look at my function and noticing right away that this is factorable. And that's really going to help you a lot, guys, if you factor first. Okay, so notice that in the numerator, you can factor out a 2. And in the denominator, we can factor. And the reason I did that is notice we have a common factor of x minus 3 that's going to cancel, which means at x equals 3, positive 3, we have a removable discontinuity. Okay, which means in the graph, what's going to be there? There's going to be a hole in the graph. Okay, and this is when I grade this prompt, and I like to do these ones with holes in them to make sure people are paying attention to the kind of discontinuity they have, because they will forget and they'll just draw the graph going straight through x equals 3, and you can't do that because g of x has a hole in its graph at x equals 3. So we will cancel to remove that discontinuity. So as far as asymptotes go, we now know, oh, we have a vertical asymptote at x equals negative 3 because it's a non-removable discontinuity. All right. And you could justify that. You could also do the limit as x approaches negative 3 and prove that it goes to positive and negative infinity. But it's fine to just say that it's a non-removable discontinuity because we know that non-removable discontinuities in rational functions result in vertical asymptotes. Let's see. How about some intercepts? How about g of 0? Well, and now that I factored, it's a lot easier, right? Because now you know it's just 2/3. Put in 0 and you get just 2/3. Where does this equal 0? It doesn't, right? So there's no x-intercepts for this one. G of x does not equal 0 anywhere. Okay, because it's 2 over x minus, or x plus 3, sorry. So we know that there's no intercepts. We know we have a hole. We know we have a vertical asymptote. I guess the last question, as I'm examining these top two before I do any derivatives, what about a horizontal asymptote? Well, if you use those rules from algebra 2, you already know, right? The degree in the numerator is 0, the degree in the denominator is 1. Anytime the degree in the denominator is bigger than the numerator, you know it's y equals 0. But we need to prove it, justify it through calculus. So what is the limit as x approaches infinity of 2 over x plus 3? Well, obviously, multiply by 1 over x over 1 over x, and you get the limit as x approaches infinity of 2 over x over 1 plus 3 over x. And these ones, 2 over x and 3 over x, these go to 0. So we get 0. So y equals 0 is a horizontal asymptote. Horizontally. I didn't mean to put a y at the end there. There we go. And that's all basic stuff that we could do without a whole lot of calculus involved. No derivatives yet, just limits. And so we've so far shown the hole. We've shown the vertical asymptote. We've shown the horizontal asymptote. So we are now ready to move on to the calculus portion. All right. So I'm going to clear this off the screen. So hopefully, if you're in here and you're following along, you have that written down if you want it. Get my chat window back up there. So I'm going to clear that in 4, 3, 2, 1. Nobody written in the chat? Okay. All right, I'm clearing it. Boom. Okay, next bit. Now we're going to look at relative extrema, and I'm actually going to do 3 and 5 together. I know I numbered them weird. I probably should have kept 3 and 5 together, and then 4 and 6 would have been smart to have together. I didn't think that far ahead when I designed the problem. So, because let's do all the first derivative stuff. So let's look at. All right. Oh, Ben got bumped out. All right. Welcome back, Ben. I don't remember what room you were in.
Neither do I.
Looks like room 2 maybe, because it's the smallest of the 3. So I'll put you back there if you want to go. All right, so first derivative stuff. Let's take a look at what is g prime of x. Well, I can find g prime of x with the form of it right now, but that's a lot more complicated than the form that I had just a minute ago. Because notice how much simpler this derivative is going to be, because the derivative of the numerator would be 0. So, when I do the derivative of the top times the bottom minus the top times the derivative of the bottom over the denominator squared. That's a lot easier, right? Because now it's just -2 over, over x plus 3 quantity squared. And so if you do it the other way, then you're going to have the derivative of 2x minus 6, and you're going to have a lot more involved in that. So again, I mentioned it with the first slide, and it's just so much easier if you factor first. So if you see the common factors, get those out of there, remove whatever discontinuities are removable, and your life is going to be a whole lot easier. And so you can just simplify your derivative life a whole lot more. So what are the critical numbers? Well, there's only one. Right? The only critical number is where this is not differentiable at x equals -3. And we actually knew that already, right? Because that was the vertical asymptote. And of course, it can't be differentiable there because the function doesn't exist there. And so that's the only place that we have to worry about. So what I'm going to do is check my sign chart here and say, all right, well, here's -4, -3, -2, -1, 0. So here's my critical number. So what is the sign of f prime of x at these points? Okay, well, f prime of x, we notice that the numerator is -2, right? And look, the denominator is x plus 3 quantity squared. It's positive all the time because it's squared. So, oh, look at that. This function is decreasing for the entire interval, -∞ to -3 and -3 to infinity. It's never increasing. So could it have any relative extrema? No, it never changes sign. So we've answered 5. We also have answered 3. There's no relative extrema. Because f prime of x does not change sign. So there we go. First derivative stuff is pretty much done. We've got the first derivative. We've seen that it doesn't change sign. We know it's decreasing the entire time. Yeah, this is so far so good. Feeling pretty good about this. Let's move on to the second derivative stuff. So I'm going to clear this screen. If you need me to leave it, just put something in the chat. But otherwise, I'm going to clear it in 5, 4, 3, 2, 1. Okay, let's clear this one. And let's get to our second derivative. So remember, g prime of x was -2 over x plus 3 quantity squared. So now we're going to tackle 4 and 6. Inflection points and concavity. What does g double prime of x look like? Well, again, because the derivative was easier by using the factored form, the derivative of the numerator is still 0 minus -2 times the derivative of the denominator, which is a chain rule problem. It's 2 times x plus 3 to the first times the derivative of x plus 3. Oh, okay, well, that's just 1. So yeah, it's chain rule, but the derivative of that is just 1. And then down here, notice we have x plus 3 quantity cubed. So let's clean this up a little bit. I've got the negative, so that's +2 times this 2, so that's 4 times x plus 3 over x plus 3 quantity. Why did I put cubed? Because I was already, sorry guys, I was a step ahead there. It's to the 4th. It's to the 4th. Now we're going to cancel one of them and get cubed in the denominator. So this one does change sign, doesn't it? Same critical, or sorry, not critical number, possible point of inflection, PPI. X equals -3. Okay. Well, it's not really an inflection point, is it? Because I know that's the vertical asymptote. I just need to figure out the concavity behavior on either side of the possible change that happens at the asymptote. So what is the sign of f double prime of x? Well, this time the denominator is cubed, so it does change sign, right? If you put in -4, right? If you find g double prime of -4, you get 4 over -4 plus 3 quantity cubed. That's a -1 cubed. That will be a negative number. So it's concave down here. Okay. What if I put in -2? What is g double prime of -2? Or how about 0? Even easier, right? 4 over 3 cubed. That's positive. So we see that it's concave down. From -infinity to -3. And it's concave up from -3 to infinity. All right. But there's still no inflection points. Because g of -3 does not exist. It's an asymptote. It's not a point. So even though there's a change in concavity, we still can't call that an asymptote. I mean, an inflection point, because it's an asymptote. All right, so here's number 6. Here's number 4. Well, gosh, we've got all of it done, right? We've found our x and y intercepts if they existed. We found all of our asymptotes. We found our relative extrema. We found any inflection points, which didn't exist. We found where it's increasing, where it's decreasing, where it's concave up, where it's concave down. I think we're ready to sketch a graph. All right, so I'm going to clear this off, unless somebody says wait. 5, 4, 3, 2, 1. Okay. Let's go make a sketch. I'll use this axis right here. So let's remind ourselves that we're dealing with g of x is equal to 2x minus 6 over x squared minus 9, which we had reduced to 2 over x plus 3. Okay. We have established that we have a y-intercept of, I took pictures as we were going along, so let me go back to our picture. We said g of 0 is 2/3. So let me plot that point on here. I'm going to use the red lines as our numbers. Like this is 1, this is 2, this is 3, this is 4, and so on. 1, 2, 3, 4, like that. So 2/3. Let's graph this in a different color. We'll put that in blue. So let's call that about 2/3 there, a little bit more than half. Okay. I also know I have some asymptotes. I've got a horizontal asymptote. Well, I'll move that so that's on the right spot. Yeah. Along y equals 0. I've got a vertical asymptote at x equals -3. I know that on the right side of this asymptote, the function is decreasing, right? Because the derivative was negative, but my second derivative was positive over there, so it's concave up. So I think I have a pretty good idea of what that looks like. It's got to, come down. Oops, that's the wrong tool. It's coming down. It's going through here. But remember, we said it had to have a hole there. Oops, that looks like it's going back up. So something like this. Well, you get the idea. It's got to get close to that line without going over it. I'll try and fix that. Like that. And then on the other side, well, I know it's decreasing because it's always negative and it's concave down. What I don't know is a y coordinate. So it might, sometimes you have to go back and go, well, let me find another y coordinate out there. Why don't I find g of -4? Okay, well, that would be 2 over -1. So that would be -2. So g of -4 is -2. So that would be down here. And then I can say, oh, okay, so it's got to probably come in and do something like this. Oops. And so that's what our graph should look like. It's decreasing the entire time, right? First derivative would be negative because this side's going down, still negative here. This is concave down, but this is concave up like a cup. There's the hole in the graph. There's the intercept, or the vertical asymptote. Here's the y-intercept. It doesn't cross the x-axis, just like we said. Yeah, this is what our graph should end up looking like. I can tell you that the kids who struggled with this one, the number one mistake they made, they didn't factor when they started. It's so important to factor it as you begin. So, all right. Any questions about prompt number 1 for you guys? Okay. All right, cool. Let's take a look at prompt number 2. Holy moly. We don't have the equation here. Okay, but remember this said for problems 1 and 2, graph the given equation. Oh, we don't have the equation, but we have everything we need. Okay, we can still do x and y intercepts. We can still look at asymptotes. We can find relative extrema, inflection, concavity, and then increasing and decreasing intervals, all from this right here. Okay, for example, what's this first line telling us? F of -1 equals f of -4 equals f of 6 equals 0. Those are all x-intercepts, right? That's what these are right here. Okay. F of 0 is 5. That's a y-intercept. And let's see. F prime of -3 equals f prime of 0 equals f prime of 2 equals f prime of 5. Those all equal 0. These are our critical numbers right here. F prime of x is greater than 0 when x is less than 0 and greater than 5. This is where it's increasing. F prime of x is less than 0 between 0 and 5. Decreasing. F double prime of x is less than 0 when x is less than -3, between -1.5 and 2 and between 2 and 4. This is concave down. So this is concave up. So let's figure out what's going on at some of these points. Like, let's take the first derivative test. Oops. So my critical numbers were -3. So let's see, -4, -3, -2, -1, 0, 1, 2, 3, 4. Oops. 5, 6. I need a longer axis. There we go. And let's mark off those critical numbers. Let's see, -3 was a critical number. 0 was a critical number. 2 was a critical number. And 5 is a critical number. So what is f prime doing around these points? Well, notice when x is less than 0, f prime of x is greater than 0. So it's increasing whenever x is less than 0. Also when x is greater than 5, so it's increasing out here. And f prime is less than 0 between 0 and 5. So decreasing in here. Look, right here at x equals 0, f of 0 is a relative maximum. Okay. We know that f of 0 is 5, so that's going to be a relative max. And then it decreases until we get to 5 again. And then so f of 5 is a relative min. Okay. Because our first derivative changes sign from negative to positive there. So yeah, right there, we figured out where our relative extrema are. We also figured out our increasing, decreasing. So we would say f of x increases on the interval -∞ to 0, union with 5 to infinity. F of x decreases on 0 to 5. And that's everything the first derivative tells us about that function. Let's check out the second derivative. I didn't give you any possible points of inflection like I did with the critical numbers, but we can still do it because if you look, we have everything we need in here. Because look, it's concave down when x is less than -3, concave up when x is greater than -3. So something's going on at -3, right? It was concave down and then up. And it's concave up when x is between -3 and -1. And then you can see from -1 to 1/2. Well, let's see, here's 0, here's 1. So here's 1/2. It's concave down. And then from 1/2 to 2, concave up. From 2 to 4, concave down, then concave up again. So we've got lots of changes in concavity. So we have inflection. At x equals -3, -1, 1/2, 2, and 4. So lots of inflection points. And then we could say f of x concave up on, let's see, -3 to -1, union with 1/2 to 2, union with 4 to infinity. Oops. 4 to infinity. And then concave down, -infinity to -3, union with -1 to 1/2, union with 2 to 4. And you can use the union symbols. You don't have to use the union symbols. You can do whichever you want. It's fine to use. Interval notation works too. So, all right. One last thing. Because of the way all this stuff worked out, I don't think we have any asymptotes. We weren't given any information about asymptotes. And so I'm going to just make the judgment that says there are no asymptotes here. With all this decreasing in concavity and stuff like that, I'm going to make the assumption that, if there had been a discontinuity, we would probably have to have been given that. But the derivative existed at all of these spots. We weren't told that it didn't exist anywhere. We similarly weren't told anything about the second derivative not existing somewhere. So that's kind of an assumption here, but I don't have any evidence to say that there would be any discontinuities. So, all right, let's make a sketch of this graph. So hopefully you have all that written down. I'm going to clear that one off unless somebody says wait. Okay. Let's put it all together on a graph. First thing I'm going to do is mark the points that we know for sure. So for example, we know f of 1, 4, and 6 are all 0. So f of, oops, get my drawing pen back. There we go. F of -1 is 0. 1, 2, 3, 4 is 0. 5, 6 is 0. F of 0 is 5. 1, 2, 3, 4, 5 up here. And then I'll use just what I know about the graph. So for example, I knew that f was increasing all the way up to 0, but there was a changing concavity at -3. 1, 2, 3. So somewhere down here, doesn't really matter where. You know, we know F was concave down, but increasing until we got to -3. So it was kind of concave down. Then it switched to concave up, and it stayed concave up until -1. Oops. And then it switched to concave down, and it stays concave down now all the way to 1/2. So, but it switches to decreasing. So I'm gonna say concave, concave down. Oh, it's so hard to draw this on this trackpad, guys. I'm sorry. Like that. And then we have to switch to concave up because our next inflection point is at 2. So I'm going to make this really exaggerated, but concave up. Good Lord, come on. And then we switch to concave down until we get to 4, but we're still decreasing. And now we switch to concave up. But at 5, we have a switch from decreasing to increasing. So now there's some kind of a thing like this. And then from 5 on up, it's always increasing. And from 4 on up, it's always concave up. So it's just going to continue on like this. And it's going to continue on like this. And this is the beast that we have described with all this stuff down below. All right. There we go. And there's one more prompt here. So let me take us to that. Oh, well, we'll fix that in a second. Where is this? There he is. So I know it's hard to read. This is the graph of f prime of x. Okay. So come here. So this is f prime of x. All right. And then we're going to look at a few things about f prime of x. What's going to be the easiest way to do it? Let me get us a copy of this so that it's, oops. There we go. And I'm going to put that off to the side. And I'm going to switch my share so it's this whole desktop. So now you can see the whole, that way we can keep the questions on the same page. For whatever reason, they don't seem to fit very well on the, there. Ah. It's a little small down there, but I think, make it a little bigger. Okay. All right, so keeping in mind that this is f prime of x right here, I'm going to actually label it. There we go. And actually, are you guys able to see everything like this, the graph and the questions there? Okay, good. I switched to sharing my desktop, but I don't have, normally on Zoom, when I share something, it puts a green border around it. I don't have a green border, so I was just wanted to double check that you could see both. Okay, so if this is f prime of x, I want you to think about it like this. If it's above the x-axis, then the derivative is positive. If it's below the x-axis, the derivative is negative. So for what intervals is the function f of x increasing? Well, where is it above the x-axis? Let's see, we got 1, 2, 3, 4, 5, 6, 7, 8. So here's -8, and it doesn't go below the x-axis until we get over here to 2. Now it does hit 0 a couple of times. It hits 0 here, and it starts out at 0. So I would say, though, that those are instantaneous zeros, so you don't need to worry about them. So increasing happens the entire interval from -8 to +2. We are increasing. Where are we decreasing? Well, 2, 3, 4, 5, 6. So from 2 to 6 is below the x-axis. So from 2 to 6. Okay, and then notice from 6 to 7, it goes back to increasing. So from 6 to 7 is also increasing. So we're increasing -8 to 2, union with 6 to 7, and we're decreasing on the interval 2 to 6. So just seriously looking at where the first derivative is positive when the first derivative is negative. A technique I like to do with these guys is to draw a sign chart right on top of the graph, because then I can transfer my zeros, my critical numbers, anywhere where the first derivative is 0 or undefined is very easy. I just say, okay, look, it's 0 here, so that's going to be a critical number. Okay. Oh, look, it's 0 here. That's going to be a critical number. And we've got a 0 here, so this is also a critical number. And then I just look, is it above the x-axis? Cool. Okay. Oh, still above the x-axis? Awesome. This is f prime, right? Oh, here's where it goes below the x-axis, and then it's back to above the x-axis. And so that's a nice technique to just say, look, here's my sign chart. So look, I do have relative extrema. I've got a relative max at x equals 2. I have a relative min at x equals 6. Now, because we only have the derivative graph, I couldn't tell you what the y coordinates are. So I'm looking down at prompt letter D there. It says, are there any relative extrema for this function? If so, name the x coordinate only, because you really couldn't do the y coordinate because you don't have that. So those would be my x coordinates. I would say, yes, we have a relative max at x equals 2 and a relative min at x equals 6. And that's really all you would need on this one, because we don't have a way to find the y coordinates. So that's down here at letter D. All right. Let's clear those. The next question says, if f of 3 is 2, what is the equation for the tangent line of x or at x equals 3? Oh, the tangent line at x equals 3. Well, to write the equation of the line, we need two things, right? We need a point and we need a slope. Well, I've got the point, right? They said it goes, f of 3 is 2. So I have the point. How can we find the slope? Well, remember, the slope is the derivative. What's f prime at 3? Sure looks like -1, right? So my slope is -1. My point is 3, 2. My equation, y minus 2 equals -1 times x minus 3. And there's the equation of the tangent line. Now that's in point slope form. Okay, if you prefer to put it in slope intercept form, distribute your -1 and then move the 2 over. That's fine. You'll get -x plus 5. Okay, that works too. But this is a totally acceptable answer for a linear equation. And that would be the tangent line of the graph. All right. So that's letter B. Okay, let's talk inflection. Okay, so that means we need to know what's happening in the second derivative. Okay, so this is where things get a little tricky, because now if I'm looking at f prime of x here, remember this is f prime. Okay, I need to know what's happening in the second derivative of f, which is the derivative of this derivative. Oh, okay, so that means, look, if we just take this section over here, let me just highlight this section right here for a second. Just right in the red box there. Notice from -8 to -6, this derivative, this graph is going up with a slope of 2. See that? I start here, I go up 2 over 1, up 2 over 1. So f double prime is 2 from -8 to -6. Okay, but then what happens from -6 to here? What's my slope? It's down 1, right? So f double prime of x is equal to -1 on that interval, -6 to -2. Aha! Look, there's a change in sign of the second derivative. Second derivative was positive, and now it's negative. And the change in sign happened when the first derivative went from increasing to decreasing. So again, I like to make a sign chart, guys. I like to make a little sign chart and say, okay, so now the possible points of inflection are going to be where there's a change in direction of the first derivative. So we already found this one right here. So let's mark that one. Okay. Where else does the second or the first derivative change signs, directions? Well, how about right here? And how about right here? And how about right here? Those are all spots where the first derivative went from increasing to decreasing. So the second derivative, okay, right, f double prime, okay, increasing, decreasing in the first derivative. So concave up to concave down. This is positive because it's going up, so it's increasing. Now it's decreasing, and it's decreasing all the way until we get out here to 5. That's 5, right? 2, 3, 4. Yeah. And then it switches to increasing. So our concavity changes up, down, up. So, oh, the breakout rooms are closing. I'm going to leave them open for just another moment while we finish this up. Oh, I accidentally hit close now. Oh, well. I didn't mean to. I meant to say leave open, but sorry, guys. I clicked the wrong button. I was going to leave you guys out there for a little longer, but we're just about done. So inflection points of the graph, there's actually a couple. Yeah. So we have the one at -6, the one at -2, the one at 0, the one at 5. So those are the inflection points. All right. And then our final question here, this one, do you think there's a vertical asymptote at x equals -2? Well, no. And the reason I don't think that is at x equals -2, if there was a vertical asymptote, think back to the first problem. What happened at -2 was that the first derivative didn't exist there, and neither did the second derivative. Okay, well, in this graph, the first derivative exists at -2. F prime of -2 exists. It's 0. Okay, well, that's not what happens at a vertical asymptote, right? At vertical asymptote, what happens is f prime doesn't exist, and the limit as you approach from the left and the right of it is infinity, or negative infinity, but it's one of the infinities. So yeah, letter D is no. There's not, and the reason that it is not is because this function is differentiable at x equals -2. We have a first derivative at x equals -2. So, all right. There we go. I'll clear that off. And for you coming back from the breakout room, sorry guys, I meant to push the button to leave you in there a little longer. We weren't quite finished over here on this side. but I clicked the wrong thing. I apologize. So we just haven't done the bonus question yet. And it's really just sketch the graph of the function from before. So if this is our derivative graph, what does the original graph look like? That was that warm-up problem that we did the other day. So let me do a quick snapshot of this, and we'll go try and make a sketch based on that graph real quick. Okay, so I know that f of 0 is -2, so I'm going to draw that point in here. F of 0 is -2. Oops. Oh, come on. And then what happens from 0 to 2 is that we increase, but we are concave down. So, and then we're gonna switch to decreasing, but we're gonna stay concave down. So it's got a curve down, but it's increasing, and then it stays curving down until we go, let's see, at 5, 2, 3, 4, 5. Somewhere here is our inflection point. Okay, and it continues to decrease, but it switches to concave up until we get to 6. So something like that, and then it increases and stays concave up forever. Going backwards from that point, I see that it was increasing and concave up, and it was a concave up all the way from -6. So 1, 2, 3, 4, 5, 6. Uh-oh, I'm gonna have a hard time with this. Like that. Then prior to that, it was concave down. Oh, whoops. Wait a minute. I'm sorry, I missed the inflection point at x equals -2. There was an inflection point here because it was increasing and concave up. But it had been increasing and concave down prior to that. And then it was increasing and concave up prior to that, so. Oh, whoops, I don't know that it does that turn. All I know is that it was increasing and concave up. Starting at wherever -8 would be, that's off my graph. So there we go. That's what my graph would have looked like. I probably could have planned that out a little better, but I'm trying to do it really quick here for everybody. So, all right, guys. That is that. I did